Nick Bambos standing here. And so I expect to hear a good talk. It's called schedule.
Cone schedules.
It's okay.
Okay. So I know that a few people have to go at 4:30, so a few. That's right. So what I thought I should do is, and it's also late in the day. I guess it's the third talk today. So what I thought I would do is kind of hop on the geometry of a few interesting problems related to scheduling around the basic model. And what I would like to bring out is basically the geometry of the problem. That's why I call them cone schedules more than the analytics. And I will give you a few hints about how the proofs work and so on. But most of those are written down already. If you become interested, then you could take a look at the papers. So the outline of the talk is the following. I will present a basic model and three applications that are in my domain of interest. Actually each one of these three areas, multiprocessing, switching, and wireless power control, have lives of their own. These are huge research areas, but at the level of modeling abstraction that I want to discuss the scheduling problem, they appear to be one unified area. And I will talk about two issues. The first one being throughput. And I will define a particular approach that I'm taking for studying throughput, and then several schedules that are essentially variations on a theme of a basic schedule, which I call projective cone schedule. And then I will talk about issues that have to do with power and cost, how to trade essentially delay and power, or acceleration, or let's say efficiency of various allocations, resource allocations in this problem that I will just define. And the problem is the following. I have several queues, and I have service combinations or service configurations or service modes. Depending on the area, different people use different terms for the same idea. So I have several queues. They could be distributed in a data center, for example, the various processing task queues. And I have resources, which could be, for example, the multi-processors, the CPUs, various resources that I combine in different ways, and I enable different service combinations. Now, if I choose to combine my resources in this particular way, which is down here, a particular way down here, I will enable a service combination, which is this one, and this will do the following. If I operate it for one time slot, say, then it will remove S1 blocks of work, let's say S1 computation tasks from here, S2 from here, S little q from here, S big Q from here. Okay? So what happens is that by combining my resources, and I will show you at least three examples, which are quite different from each other. So if I combine my resources in particular ways, I enable different service combinations, and then the problem is to choose at each point in time a service combination, a service vector actually, to use in order to do good things to the system. So the first good thing that I want to do to the system is maximize its throughput. And the question is, how do I define throughput, and how do I define the schedule for choosing these service combinations at each point in time, given the backlog that I see in the queues, or even the history of the backlog, right, and the history of the service choices that I have made in the past. Now, another issue or another good thing that I could do to the system by choosing carefully is to trade off power for delay, because actually different service combinations could be associated with different costs or different powers, right, in order to get them enabled. For example, it could be that on the right, as I go more and more to the right, I get faster combinations because I pay more or I burn more power in my processors. Actually, this is exactly the system that I have in mind. Let me show you a few examples. So here's the first example. It's the simplest in the class of multiprocessing. So I have two computation tasks, and I have three processors. So I can put all three processors here, and then I have a service combination which is 3 and 0, or I can distribute them differently, let's say 2 and 1, 1 and 2, or I can slow this one down, this processor down, or I can accelerate it. So I can get all kinds of combinations, and one of the problems is that I get too many combinations, obviously, because all these combinations could explode combinatorially, factorially, and I will have to deal with this type of complexities. But it's clear that this could describe what could be happening in a data center, on a rack, on a data center, for example, in a data center. So multiprocessing is one area. The other area is switching. So let's take the following point of view. What is a switch? A switch is a box that has input ports and output ports. Now, all that it does is that it has packets showing up at the input ports, and they want to go to some output port. So what I'm going to do is I'm going to put in this queue all the packets that arrive to input port 1 and want to go out here to output port 1. I'm going to put in this queue all the packets that arrive to input port 1 and want to go out here, right, from there to here. Then in this queue, all the packets that arrive to input port 2 and want to go to 1, input port 2 want to go to 2. Now, the only thing that the switch cannot do is that it cannot send 2 packets at the same time to the same output port, because their electrical signals would collide and they would evaporate. They wouldn't be able to decipher which was what. Now, if I vectorize this system, actually, since I want to do geometry and describe the geometry of these schedules, I tend to also go towards constructing vectors as opposed to matrices so that I can do projections and the like. So I can set the switch in this configuration where it will transfer a packet from here to here and from here to there in one shot. And then I will be serving these queues with this service combination. Or I can put it in this configuration, and then it will be serving the red queues there. So this is, again, the simplest example in its class, because this could scale into an n by n switch. Okay. Here's another problem. So this problem alone, the switching problem, has a huge literature associated with it, has a life of its own. Okay. Here's another problem, which is the wireless power control problem. Now, what's happening here is that, again, I have queues which are associated with the input queues or the transmitter queues of wireless links. And what happens is that I can choose the power to transmit at every point in time, right, from the transmitter to my intended receiver. But of course, all these links are interacting in the same channel. And if I set the powers, then I will see a certain service combination, a certain service vector materializing. So actually, in this case, I cannot directly choose the service combination. The only thing I can do is actually choose it or enable it, drive it, by choosing the powers to set at the transmitters of the links. So to become a little bit more specific, really the service combinations or the service vectors are generated by mapping the power vector that I choose here through some function. And this function would depend on the topology of the links, the particular technology that I'm using, modulation, coding, and all these things, right? So I don't know exactly what this function is until you give me the particular system that I'm dealing with. Now, if I do this, so under this perspective, essentially, if I have just 2 links, and this is my power box, so I can choose a point here, and that would correspond to setting one link to this power and the other link to that power. This will map to a rate or a service rate vector here, where this link will be getting, link 1 will be getting that much rate, and link 2 will be getting that much rate. And of course, depending on this function that maps the power vector to the service vector, right, I may get rate regions that are like this or like that. And again, this problem itself has a life of its own, right? There's a huge literature in power control for wireless systems. So these are three seemingly different areas or seemingly different problems that get unified under the model that I showed you at the very beginning. Now, so this means that it's worth studying this model in various ways. Now, what are the core implementation and operational issues associated with this model? First of all, complexity. I have to deal with complexity because typically I have many, many more service vectors than I have queues. And I'm thinking of hundreds or thousands of queues, but trillions and trillions of service vectors. And that would be the normal thing to have. Now, another thing that I want is robustness. So if I design an algorithm which is not insensitive, let's say, to model uncertainties, or if I change a little bit the system, the algorithm would collapse as opposed to still keep operating well, then it would never be implemented. So I want I have a goal to design something which is as robust as possible, and it's insensitive to various particulars of the system. For example, what if I have switching times? To go from one service combination to another service combination, I need to spend some dead time. What if I have unreliable state information? So I think I'm operating the system based on backlogs, backlog information that was given to me, and I think that this is current, but this is actually delayed, or there are lots of errors and so on. What if I have, I don't know exactly the statistics, or I don't have a model for the statistics of the traffic? Various things like that, right? I want to be robust and insensitive to particulars. And finally, the ordering, so to speak, of my concerns is first to look at throughput. This is very common actually in all these queuing systems. First to look at throughput, then delay and fairness, which I will not address today, and then I will talk a little bit about cost optimization, but first throughput. So let me deploy first the perspective that I take, the approach. Now, I want to operate under arbitrary traffic traces, including traffic traces that may be adversarial. So let me explain what this could mean. So imagine that I have someone that generates the trace, and the system or the operator of the system uses a certain strategy in a game theoretic context, and I even know the strategy that the scheduler, the operator of the system, is using. Can I generate a trace which is so bad that I can drive the system unstable without even loading it too much? So this is what I mean by adversarial, and in the course of this talk, I will show you examples, and it will become clearer where this comes from. Actually, there is an area of queuing called adversarial queuing theory, which was I guess pushed a few, when was it? I think around 90-something by John Kleinberg at Cornell and a few other people. So this is motivated, this adversarial trace is partly motivated by that. So I want to have very general traffic traces, which could have jumps, could have continuous flow of work, could have jumps here, and could also have delta jumps that could correspond to arrivals of jobs at points in time. Now, the least I need is some concept of load, right? Because I want to study the throughput of the system. So I'm going to define in the lightest possible way some concept of load. And the concept of load that I'm using is that essentially there is a long-term average of this traffic trace for every queue. Okay, so this limit exists. Actually, even that I can lift and go with limit soup limbs and limb soups and so on, but let's stay with this for the moment. Then I need some kind of an extremely light version of what I mean by stability and throughput. And the concept I'm going to use is the following. I want the departure rate to be equal to the arrival rate. So whatever goes into the queue comes out of the queue. I don't have a flow deficit which accumulates in the queue and eventually will in the queues and eventually will get them to blow up. So my concept of stability is essentially flow conservation. As long as I have long-term flow conservation, I'm okay. And practically, mathematically, what this corresponds to is having the backlog divided by t, as many of you know, going to 0, which, if you haven't played with that before, it could be quite misleading because it could grow square root of t, right? But still, this is a firm, very light, though, concept of stability. If I start imposing on the problem heavier statistics, or even probability and statistics on these traces, then I could kind of tighten up the concept of stability far more. But I don't want to do that because I want to stay extremely robust, right? I want to study robustness of these algorithms. So I want the lightest possible assumptions for the moment. So again, two main assumptions. There is a concept of load, this, and a concept of throughput, which is this. Now, what is my point of view? My point of view is not a stochastics-related point of view, but comes from the theory of deterministic dynamical systems. And I'm viewing the system as being driven by this trace and the scheduler controlling the system, and everything is deterministic. There is no probability at this point. I can bring probability later on into the game, right, but not yet. And as I was saying before, it's also related to this adversarial queuing theory strand of research. So if I were to look at the stability region, or this is my load, and these are the service vectors that are given to me initially, part of the system, part of the specification of the system. So I take all these service vectors, I put them on this graph, and of course this is a two-dimensional, but it could be n-dimensional. And then if I'm in this little box, which is defined by the service vectors, then the question is whether I can find some kind of an algorithm, some kind of a scheduler that would keep the system stable, meaning it would preserve flow I would have flow conservation. Actually, it's easy to see that if I'm outside of this box, there is no hope. At least one Q will give and will blow up. But if I'm inside of the box, then the issue arises whether I can find a scheduler that can keep the system stable universally. And what does that mean? It means that any trace that you give me and any service vector set that you give me, this particular policy that I need to design would keep the system stable. It would preserve flow conservation. Think of it like this, at this level of pre-probability, so to speak. Okay? So this is the setup of the problem. And this is a congested slide. Let me walk you through it little by little. So instead of, in order to make a long story short, let me show you what algorithm would do that, right? And the algorithm that would do that, I call it PCS, projective cone schedules. Basically, all it does is that it looks at the current backlog of the system. Then it applies this B matrix, which I'm going to explain in a minute. And then it looks at all the service combinations, and there are plenty of those, right? So there is a complexity issue here. All the service combinations, and takes each one of them and projects them on this BX, and looks at the one, picks the one that has the maximum projection. So basically, if you want to think of it geometrically, what happens is that I have this backlog vector, then I hit it with this B matrix, so I will twist it and stretch it, and then I take every S, I project it on this twisted X vector, and I take the one that has the maximum projection, okay? So if this B matrix were identity, in which case, I will talk about that in a minute, you recover essentially the well-studied maximum weight matching algorithm. If that were the case, basically what the algorithm would do is look at the backlog profile of the system and try to find the service vector that is the most aligned with it, and it's the most intense, right? This would give you the maximum projection. So projection, maximum projection, has a flavor of alignment. So that's kind of a good geometric message that all you are doing essentially is trying to align your service profile with your backlog profile. And that's part of this projection mechanism up there. Now, what is the role of the B matrix? Now, the B matrix, in order for the system to remain stable under this algorithm, meaning to be flow conserving, if I am in this box that I defined before, this box here, and this is essentially the box which is defined by all the service vectors, right? I put them in this n-dimensional space, and then I look at kind of the convex hull, right, including also the projections to the axis and this point there, and that's really the box, which is, this shows up quite commonly in almost all queuing systems, one way or another. But again, what I'm looking for here is that if I'm outside of the box, then I know it's impossible to find an algorithm to keep the system stable. If I'm inside, the question is, can I keep it universally stable, right, for all traces? Okay. Now, the B matrix there, so this algorithm would do it within a class of B matrices. And the B matrices have to have the following properties. They have to be positive definite, need to have negative or zero off-diagonal elements, and they need to be symmetric. As a matter of fact, positive definite is an essential property, because if you give me a B matrix which is not positive definite, then I can find a system of S's and a trace that would drive it unstable. That's kind of the flip side of the universal stability that I was defining before, right? So you give me a B matrix which is not positive definite, then I can find a system, right, of appropriate dimension, a set of S's essentially, and a trace, right, that would drive the system unstable. Same thing with the negative or zero of diagonal elements. If you give me a B matrix which has a positive off diagonal element, I can construct a set of S's and a trace that would drive it unstable, even though the load of the trace is down here. So no matter how small the load of the trace is, right, within this box, I can still find an adversarial trace and a set of S's such that the system would be unstable, even though I'm inside the stability region. So this is not, let's say, the usual way we view queuing systems, but it's more, that's why I brought up this adversarial queuing view. Now, the symmetric property, for this we don't have a counterexample. I don't think it is absolutely essential, but for the current proof that we have, it needs to be there. But since we couldn't find a counterexample, I cannot say that it has to be there no matter what. The other two have to be there no matter what. Actually, as you will see later on, it's not the PCS algorithm itself that I'm dying to analyze. It's basically the robust relaxations of this algorithm, because the PCS algorithm itself is quite difficult to implement. I have to search over a huge set of service vectors in order to find the one that would have the maximum projection. And when I say huge, I mean trillions and trillions and trillions, right? And that I couldn't do within nanoseconds where I have to make a decision in a switch, okay? As I said before, if you set B equal to I to the identity matrix, this essentially reduces to the maximum weight matching algorithm, which is very well studied, starting from Tasciulis and in various contexts. Markovian, fluid, this, that, many different contexts, starting from Tasciulis and Ephremidis, McEwen, basically all our friends, one way or another, and many more actually that I couldn't include there, are there. Now, what is the role of B? Actually observe that the B matrix essentially gives me Q squared. If I have Q's, right, I have Q squared knobs to play with. So if I were to change the B matrix and set it to different values by changing the knobs, then I would be able to trade quality of service between the various Qs. Delay, this, that, and so on. Jitter, various aspects. So essentially, think of one particular aspect which is interesting in this PCS algorithm is that you have plenty of knobs to tweak. It's very robust, as you will see later, and it has interesting geometry. And let's start with the geometry. So what is it that I'm doing essentially? Basically, I'm maximizing this quantity. And look, if I scale up the backlog of the system, so if a particular S maximizes this for a particular backlog, and I scale up the backlog, it's going to be the same S that will maximize it again, right? Why? Because the scalar I will be able to pull out of the inner product. So that means that if I kind of geometrize this schedule, all that it does is that it splits the backlog space, right? This is the backlog space, right? 2 dimensions and several others here, into cones, multidimensional cones. And then what it does is that it says, okay, if you are in this cone, the red cone, then you are always using this particular service combination. If you switch or if you float into the green cone, then you have to change your service combination, okay? So if I were to construct some kind of a lookup table and forget completely about the projections and all these things, right? I could think of a class of schedules that are conic, and they are described in the following sense. I look at my backlog, I go to the lookup table, and I say, okay, where is my backlog? Which cone is it in? And then by identifying which cone it's in, then automatically I know which service combination to use, right? So one issue is what is the largest class of cones, irrespectively of these projection things that I was describing before, that would maximize the throughput of the system. So this is a geometry, and actually by playing with the B matrix, what I can do is actually move the cones around, obviously. So here is an example, a little example of 3 queues. That's why these are 3-dimensional. And actually what you are seeing, these are 3-dimensional pictures, and the cones are kind of coming at you, and they are cut by the screen, by the plane of the screen, right? And what you see is basically the cross-section of the cones with the screen. So you have 3 dimensions, and you have 4 service combinations, these up here. Now, if I choose the B to be diagonal, then these are the cones that show up. And if you are in this cone, you will be using S4. If you are in this cone, you will be using S3, S2, S1, and so on. If I start tweaking the B matrix, then what will happen is that I will be tilting the cone, the central cone, and of course all the others, right, in certain ways. And by doing this, I'm not going to elaborate more on that, but essentially I'm suppressing the quality of service of certain queues, or enhancing the quality, and at the same time enhancing the quality of service of other queues, just by playing with this B matrix. Now, how do we handle complexity? Actually, there are 2 ways of handling complexity, and complexity is a big problem. So let me show you one way to reduce drastically the complexity. And again, sticking to the idea of the cones. Now, imagine that your backlog is here. And imagine that when an arrival occurs, it is bounded. So it cannot push you off your current point beyond a certain region, right? So you are here, an arrival occurs, you will be somewhere in this ball, right? Multidimensional ball. Now observe the following. Since these are cones, if your backlog is very low, then this ball will be cutting, right, touching many cones, which means that you have to search over all these cones, over all these vectors that correspond to these cones, to find the one that will give you the maximum projection. Not good, because the cones that you have here are trillions and trillions. But as the system gets more and more congested, this ball essentially, right, moves further and further out. So now you have you are congested now, you have a high backlog, you get hit by an arrival, you still live in this sphere, multidimensional ball there, but now because these are cones and the cones grow up, like grow more and more linearly as you move out, but this ball is not growing, eventually you will be touching only your neighboring cones. Does that make sense? So when you become congested, you don't need to search over all vectors that correspond to all cones, but only you need to look at the vectors in your neighboring cones. So let's change the algorithm in the following way. So here's again, the cones are coming at you. You know, the tip of the cones is behind, and you're looking at the cross section. And this is cone 1, where if you happen to fall in this cone, you need to use service combination 1. If you are in this cone, the thing to use is service combination 2, and so on. And now let's construct a graph. So I will represent each cone with a node of the graph. And if 2 cones touch each other, they are neighbors, then I will draw an edge between the node that corresponds to this cone and the node that corresponds to this cone, just because they are touching each other. So eventually we'll have a graph like this. So imagine that currently I'm using this particular service vector, right? And this is the service vector to use anyway. But suddenly I get hit by an arrival pattern, right? New arrivals that push me essentially out of this cone into, let's say, this cone. Now, what I should have done, according to the strict PCS, is that I should have looked at all the nodes, right, or all the cones, all the service combinations, and find the one that gives me the maximum projection. But I don't need to do that, because actually the only ones that will be relevant if I am congested, and since we are talking about stability, it's the congestion, the high congestion regime that matters. All I have to do is basically look at my neighbors. And I have way fewer neighbors than the whole graph and the whole number of cones in there. So essentially, I'm doing a walk on this graph where I'm here. I'm looking only at my neighbors, and I choose the neighbor which gives me the maximum projection, but within the set of my neighbors. So essentially what I'm doing, I'm climbing gradually upwards. Right? If you think of this as a potential surface, right, which depends, of course, on the backlog, or where my backlog is and so on, I'm kind of doing steepest ascent, right, gradual steepest ascent. Of course, this is one way of reducing the complexity, right, because I have tons of cones, but I may have only a few neighbors next to me. Now, let's think of other aspects of robustness. What happens if I have unreliable state information? So the backlog information arrives to me with delay. And as a matter of fact, on top of that, some of the some of the bits have flipped, and there is noise also. Is the algorithm robust with respect to that? Actually, it is. So no time to go into the, actually you will see it from the proof. I have a slide with some ideas on the proof. What if I have switching times? Switching times would mean that I'm here and I need to use a service combination which corresponds to this cone, but then I get kicked by an arrival here and I need to use a different service combination. What happens is if there is a switching time, so that switching from service combination to service combination, there is some dead time. And imagine a pattern that would do this. Then I would never do any work at all. So in order to get this to work, you need to introduce some kind of sublinear, a certain type of hysteresis. Because if you don't, I can generate an adversarial trace that would get you stuck forever, and you would explode on exactly this line. That would not happen, of course, if you are flipping coins and things like that, right? But here we are not flipping it. It's a trace that I gave you, right? And I'm as bad as it gets. I can be very adversarial to you. Okay. Finally, there is a or the level of robustness to which we have studied this problem is what we call delayed PCS. And delayed PCS means the following. So when I enter this cone, so imagine that my backlog fluctuates, and at this point, I enter this cone. Now, when I enter this cone, I should be using a certain service combination which corresponds to this cone, which gives me the maximum projection, essentially, to my B multiplied by the backlog vector. But I'm going to relax that for practical reasons. And what I'm going to do is impose the following condition. If I enter this cone and I stay in it for more than t seconds, where t could be 10 to the 80th, as large as it gets, as you want, but fixed, right? Large but fixed. So if I stay in there for more than time t, then after time t, I will be doing the right thing. So I can fool around, right, and try to find my way around when I get into this cone, but only for t seconds. Doesn't really matter how big t is, but it has to be fixed. Okay? After t, I need to recognize where I am and do the right thing. So that opens up quite a lot of room to maneuver in terms of designing algorithms for implementing this type of schedules in practical ways. Let me show you some idea of what the proof is. So basically, you argue by contradiction, and you look at, you divide the backlog by t on both sides here, and you want to show that xt over t, as t goes to infinity, goes to 0. That's basic. That would guarantee flow conservation. Right? So because the B matrix is positive definite, you want to show that this whole thing kind of crashes to 0 eventually. Right? Now, arguing by contradiction, you say, okay, let's assume that it doesn't crash to 0, but there is a subsequence which hovers above 0. I'm going to look at the subsequence that generates the maximum, the lim sup, the maximum hovering above 0 of this quantity there. And I'm going to extract the vector u on which this explosion occurs, right, of the xt, such that xt over t doesn't go to 0, but it goes to a particular u. So what is happening is that the backlog of the system essentially floats around, but from time to time, it kind of touches this axis or comes very close to this axis u, which is the direction of maximum explosion for this quantity there. And then it's easy to see that if I write the backlog at this point, and of course all this has to work on subsequences, right, in the general case, because I could be coming in and out and then go out again, come in, and so on. So it's a game played on the subsequences. But actually what happens is that I look at the workload here, at the backlog here, and the backlog there. I take the difference. This would be equal to the workload that arrived during this traveling from the boundary of the cone to this u, minus the service that I produced, right? Or the algorithm, the PCS algorithm produced. Then I project this on BU, right? And this on BU. And what I get, after a little, taking the limits and the subsequence and so on, I get this, which actually by rho, the load vector being in the stability region, this has to be negative, which means essentially that I couldn't, the point where I enter is kind of higher than the point where I hit this u direction, right, as I come again and again and again into this cone. So I kind of assumed that the maximum explosion was happening on this direction u, but actually I find through that the maximum explosion is happening on the boundary of the cone, and that's the contradiction, basically. The reason being that when I'm exposed to the service vector that is appropriate for this cone, this service vector is pulling me faster than the arrivals are pushing me out. And because of that, this trend, so to speak, is always that I start from a higher point and I go to a lower point. If I kind of draw a circle, so to speak, starting from here, or a ball starting from here, and looking at what distance is this point and at what distance is that point. So it's a fairly geometric, the proof, as it should be, as with all this geometry in there. So very quickly, I spent more time, I see, on the throughput discussion. But let me tell you about the trade-off between delay and power. So going back to the same model, I want to study now the trade-off between the delays here and the costs of the service combinations. So think of having associated with each service combination a certain cost, for example, power. Let me give you a particular example to make it very precise. So let's go back to the switching example that I was discussing before. So again, I have the queues. I have two service combinations. If I set it into this configuration, then the first queue will get service 0 for all these service vectors. If I set it to this configuration, it will get service 1. Now the difference here is that I can accelerate or decelerate the service combinations, meaning I can crank up the power in the switch, which is a cost for me, right? I don't want to be burning lots of power, right? Because it will melt the chips and all this for various reasons, right? For green tech and all this, but even beyond that, it's very expensive actually to be running a switch at very high power, and especially to be turning it up and down. I mean, cranking it up and cranking it down all the time, even for reliability reasons. The chip will melt or will crack very soon. So what I'm doing is I have the various service combinations. You see, they have the same pattern, but they have higher speeds. So the hot service combination removes in one time slot 4 blocks, 4 packets from there, but the cool service combination removes 1 block from there. So really, this is an example of a more general problem where I have service combinations that are faster, let's say to the right, and slower to the left. Now, if I get hit by a burst of packets, what should I do? What I should do is actually go to a faster service combination, drain them fast, right, and then relax back to the slow service combinations. Okay, I mean, that's natural to do. So if you were to do that formally, then eventually it would be some kind of a dynamic programming problem, which smells intractable, right? So if you are to solve it completely, it's not easy to do. You have to go into some type of approximations. Actually, another point of view which is relevant is the following. Imagine that you have the cool service combinations, which are these, and you have the hot service combinations, which are these. So if you activate the cool service combinations, essentially this is your stability region, your throughput region, right? Any load in this blue region, right, defined by the blue vectors, would be stable. Now, if your load comes closer and closer to this boundary, what do you expect to happen? You expect actually the backlog to increase, right? Because you are stressing the system more and more, and you are using the slow service combinations. So if this drifts close to this boundary, you have the option at some point to actually switch to the faster service combinations and actually, enlarge your states, your stability region, right? Get further away from the boundary, hence reduce your backlog. So that's basically what is in operation there. Now, knowing that it is a dynamic programming problem and difficult to solve, we have been looking for let's say, relaxation, so to speak, or special cases. And it turns out that there is a practical special case where you can use particular costs that do make sense, and the problem gets reduced to a linear quadratic regulator problem, which is a problem control theory which exists since, I don't know, 60s or even before that, I'm sure. right? A Riccati equation pops out. It's in books. You can see how to solve this particular case. The interesting message, though, is the following: that in this special case, what happens is that you can decouple the two decisions that you have to make. And the decisions that you have to make is the following: what alignment to use, or what service vector class to use, this or that, and then how fast to go. So there are two decisions. When you look at your backlogs, in general, you're thinking, should I be using this service combination, connect, for example, these input to output ports, and then if you decide, let's say this one, how fast should I go? Now, to optimize in this particular case, all you have to do is still use the projective cone or the maximum weight matching algorithm, which essentially all it does is that it aligns the backlog profile to the service profile, as we were discussing before. And then you choose the speed mode, how fast or how deep to go into these service combinations. And this is a function of the total backlog. So first you take care of alignment, aligning the service and backlog profiles, and then you take care of congestion by accelerating your choice, right, your service vector, so as to match essentially the total backlog. And it's the total backlog that matters, which makes it very practical. I have some simulations. Perhaps I have some time to explain that. So here I'm comparing the maximum weight matching to the power-aware maximum weight matching that I was describing before. And on this axis, you have the power, the average power burnt. And on this axis, you have the backlog cost, or the average backlog. And really the total cost that gets into this dynamic program, the special form of dynamic program, which is the LQR, has two components, the backlog cost and the power cost. And it has a factor here, alpha, which actually shows how much I value power versus backlog. And I'm simulating here for different values of the weight of power versus the weight of backlog. So you see that if you take this curve, for example, as I drop my power, so if I'm power sensitive, this means that I have to tolerate higher backlog. That makes sense, right? So if I'm not willing to spend a lot of power, then I will have to tolerate higher backlog. And the knob that I'm turning actually to climb up on this curve is essentially this alpha here, okay, or to move around on this curve. Now, the different curves correspond to different loading of the system. Because if I'm loading the system more and more, right, I'm more and more into the congestion regime, and then this trade-off of backlog versus power becomes more and more difficult to manage. Now, the power-aware, the maximum weight matching algorithm would essentially use always maximum power, right? The standard maximum weight matching algorithm would always use the fastest combinations. That's the current technology, right? Use the fastest combinations. You cannot actually scale down or reduce the speed of the circuits in older technology, so to speak. So that's basically what is demonstrated here, that as you stress the system more with respect to higher load, higher arrival rate, then this trade-off becomes more difficult to handle. But the maximum weight matching algorithm would always achieve the minimum delay, the minimum backlog, but at maximum power. But the power-aware maximum weight matching would allow you to trade, right, between power and delay in a systematic manner in this particular LQR environment. So finally, so this family of algorithms is throughput maximizing. This is good news, even in the case of adversarial behavior, right? where essentially the adversary knows how you are playing and is trying to destroy you, right? Cannot destroy you. It's very robust, and because it has lots of knobs, it provides opportunities for controlling the quality of service and trading off quality of service between the queues. Now, one issue is how should B, the matrix B, be controlled? Right? There is no complete theory for that. I mean, simulations do show the effect. You change a little bit the manager, so to speak, chooses a different B. Automatically, you can see the average backlogs in the queues dropping or increasing, and after a while, you figure out how to do that for small systems. But there is no complete theory up to this point for how to do that systematically. Now, what is the most general class of cone schedules? The cone schedules that I was describing were all generated from this projection thing, right, the PCS. But I could think of cone schedules irrespectively of that, right? And the question is, what is the largest set or the largest class of algorithms, of cone algorithms, right, that would stabilize the system? What is the key property in operation actually which is hidden by looking at this particular way of generating the cones? And finally, for the last, for the power issue, that's a killer problem these days in data centers, in high-speed switches, and so on. How do you trade backlog or delay with power? It's not a trivial thing to do, and of course, you want to do it in a way which has very light overhead. Hence, you can implement it, right? Because if you go into a fully dynamic programming and so on, then it's impossible to run. So I will stop here, and thank you for your attention.
Maybe I have one remark. I think you were just asking what are the cone policies that would stabilize the system whenever it's possible. I think we solved the problem with two classes. And basically, these are all the cone policies that basically the stability region is defined as a contour of the vectors that are effectively scheduled. So such that the corresponding cone is non-empty. And so basically, if the contour is actually describing the convex wall of everything, then it's the entire stability region. If you have a point that is below the let's say Pareto boundary of the convex wall, then you are not stabilizing the system whenever possible. And for larger system of queues, I think we have also some ideas, but
I think the trick, since you mentioned it, is the following. So by looking at this problem ourselves, I think the trick is as you build these cones, these arbitrary cones, not to violate the order, the natural partial order that the most extreme vectors, as you call them, the profile have in the multidimensional space. If you, for example, define a cone here which has a vector in it, A, and a cone here which has a vector B, but when you are in this cone, you use this vector, then you can topple the system and it will explode.
Yes.
So that's...
Yes. Also, I mean, a lot of utility maximizing allocations could be seen as cone policies, but they don't have the right stability properties because of what you said or because of what I said in the case of two dimensions.
They are not fully compatible, right? Maximizing the utility and maximizing the throughput. These, depending on how you do it, they could be incompatible objectives. They are not necessarily compatible. And I think there are a few papers, Mang Chiang and a few other people have looked at, and I think you have looked at that too, right?
Yeah. Is there an idea of implementing PCS in distributed manner, or I mean, how distributed can it be?
Good question. So, for the incarnation of PCS in the wireless case,
you mean with power control? With
power control, that's right. In that case, it's again. Some of that we're wondering ourselves, but there is a very rich literature regarding distributed implementations of that in some cases, right? In some other cases, we hope, me and Alexander, but we're not there yet. Now, for the case of the suites, why would you want to implement it in a distributed manner? Because you have all the information locally.
Yeah.
Now, you would want to make it faster, right? To make the decision faster. And frankly, at that I haven't looked at. However, there are, again, the approach that we have taken is to look at the relaxations of the algorithm that maximize the throughput by making, but they make suboptimal choices of the service vectors. Of course, something has to give there, right? If you don't put in the effort to find the optimal vector, you pay in some other way, which is additional delay, right? So the more suboptimal you become, the more delay you incur, but you never lose throughput. So throughput is an extremely loose property, so to speak, right? It's very robust. It's very difficult, unless you do something really bad, to get it to break. Now, controlling the backlog or the delay, that's a much more subtle kind of a thing.
So actually, so what you are speaking, you said you will add some probability, but it's essentially for the deterministic systems. You may introduce.
Yes. Up to this point, yes. So the deterministic, exactly. Thank you very much for bringing this up. Everything I did up to here is a completely deterministic system. Even if I knew nothing about probability and so on, it's there, right? So the question becomes, what happens if I start putting probability on top, right? As a matter of fact, the first thing to observe is that if I had the stationary ergodic input, for example, this property with the arrow would be kind of automatically be generated. But I would have a much more, which I don't need. The next question to ask is how much of a probabilistic structure do I need to put on top so that this very loose concept of stability, which is rate stability, becomes tighter and tighter and tighter, and eventually something which is very close to the stochastics we're used to, right? And I think Jim Dye has looked at how do you go from rate stability to Harris recurrence by putting on top of not for all systems, but for certain systems, by putting conditions, right, on the statistics of the arrival process, so that if you get rate stability initially, that guarantees automatically Harris recurrence. Actually, in this line of discussion, I have been going in exactly the opposite way, right? Away from probability and more towards adversarial queuing theory, right?
No questions. Thanks again.